Hello, good afternoon. So we are going to start today's class in 5 minutes. So let's start today's session.
Yes, good evening, ma'am.
Good evening. I hope my screen is visible. So the first question is fluidized bed is a multi-phase system. Is it true or false?
True.
Flu yes, the answer is true because it fluidized bed means it consists of gas, liquid,
Solid liquid.
and solid. Gas, solid, and liquid solid. So this is true. Next. In fluidization, what are the dispersed and continuous phases? In fluidization, what are the dispersed and continuous phases?
Ma'am, continue.
In fluidization, what are the dispersed and continuous phases? So, gas or liquid acts as a continuous phase and solid as discrete or dispersed phase. Because in fluidization bed, you have noticed that liquid is coming from the bottom portion and there are solid particles inside it which are floating and sometimes gas is also there to create bubble inside the fluidization bed. So gas or liquid is the continuous phase and solid is the dispersed phase. Next, fluidized beds have a which kind of pressure? It has pressure head due to gravity. Fluid, fluidized beds have what kind of pressure head due to gravity?
Static pressure.
Yes, the answer is static pressure. Next, the hydrostatic pressure inside fluidized bed decreases with the depth in the bed. Is it true or false?
False.
Yes, because it rises. Hydrostatic pressure inside
Right.
fluidized bed rises with the
Depth
depth
in
of
the
the
bed.
bed. Next question. Explain the different flow patterns in fluidized bed. So that is the what type of
Edge of the
yes. So initially what was that? Suppose this is the first one is the fixed bed or packed bed. So here the liquid is filled and it is not moving. It is coming from bottom and it is fixed and there are particles inside it. So it is not moving. This is called fixed bed.
text.
Now in the homogeneous bed, the liquid velocity is little bit increased. Liquid velocity is liquid bit increased. So this fluid and inside the particle started mixing with each other and creates a homogeneous mixture inside the bed. That is called homogeneous bed. Next one is the
Bubbling.
bubbling. So in bubbling bed, what happens when now the
Liquid.
liquid or gas velocity is
Low.
further increased. So here
Yes.
it was very low, then it is increased here, then it is increased even more here. So what will happen because of the solid particles are there, because of the particles and this high velocity or gas velocity, the gas will create some bubble inside it. So that is the bubbling fluidized bed. Yeah, that is a bubbling fluidized bed. Next comes if the bed height is very long and the diameter is very low, then this bubbling blade is called the slugging. The same
Yes.
phenomena, but when this here the bubble size is a little bit bigger as it goes upward, and solid particles are there and liquid or gas is coming from here. This is the slugging. Next comes the liquid velocity is further increased. Liquid velocity or gas velocity is further increased. So what will happen? It will create some chaotic kind of motion. So it will create the bubbles will burst and it will create some chaotic kind of motion inside it. So particles are there and it will create the fluids or gas will create some chaotic kind of motion. So that is called the turbulent bed. So now it has
Sir.
become the turbulent bed. And after some time, what will happen if we keep increasing the velocity of the liquid inlet? So after some time, what will happen? Some bubbles will be there or chaotic motion will be there. Some solid particles will be sprouted out from the bed. So what is called? This is now if some particles which are in the top position of the bed, they will be thrown out of the bed. So that is called the fast fluidization. Fast fluidization bed. And after the fast fluidization bed, if you notice that if suppose all the particles are thrown out in the fast fluidization bed, almost all the particles, then the particle density or particle concentration will be very less inside the bed, right? Because most of them are thrown out of the bed. So very less amount of particles are left in the fluidized bed, and that is called the pneumatic transport. That is called pneumatic transport. So these are overall the different types of flow patterns in the fluidized bed with respect to the liquid or gas velocity. Next questions. Explain the contacting method of in fluidized bed. Explain the contacting method in fluidized bed. Explain the contacting method inside the fluidized bed. So inside the fluidized bed, how particles are contacting with the fluid and how fluids are contacting with the solid particles and how the mixture will work, that is they are saying. So it is not always that fluid is coming from top, fluid is coming from bottom and solid is coming from top. It is not like that always. So in all, suppose this is a batch process. It can happen in five different method. That is the batch. First one is the batch process. Okay,
Yes, ma'am.
so at a time, some amount of solid particles are given inside the bed, and there is a limited amount of fluid is there, and the fluidization process is happening. In the mixing is happening. Next one is the co-current.
Okay.
Next one is the co-current. In co-current, that liquid is coming from the bottom and solid is also inlet from the bottom, and it will start mixing and both of them will taken out from the top. So this is co-current. Next one is the counter current. So from the name itself, it is very clear what is it. So here the direction of inlet and outlet are opposite. From suppose from bottom liquid is going in and from top solid is given inside the bed, and now liquid is taken out from the top, liquid out, and from bottom solid is taken out. So this is the inlet and outlet positions of solids and fluids are opposite. That is the counter current. And inverse means both of them are coming through the opposite direction. Liquid is coming from here, solid is coming from here, and they both of them are taken out from here. So this is the whole system is reversed. That is called inverse. And last one is the cross current. In cross current, it is not a vertical, rather it is a horizontal fluidized bed where there are multiple inlets and liquids and solids are given. Suppose solids are given from here, and for multiple inlets, fluids are passing inside the bed, and it will create a mixture. So solid particles are there, and after the fluidization, it is collected from here. So this is the previous ones all are the vertical bed. This is the cross current. In case of cross current, it is the horizontal bed. Okay. So
Okay.
next question. Explain the different types of fluidized bed. So we'll see one by one the videos of it. That just I have told what are the fluidized bed, and we'll see from YouTube, so it will be more clear. So So here you are seeing this is a fixed bed. So the whole system is fixed and the fluids are coming from top, and it will start mixing. That is the fixed bed. This one is the fluidized bed. So these are the different parts of the fluidized bed, and so particles are given, and with the pressure of this valve and all, pressure is created inside the bed and the fluidization will start. So you can see that due to the gas or whatever is inside it, because of that, solid particles are trying to mix with each other. So this is the fluidization. Fluidization in general. Then this is the bubbling bit. So just now I have told that why bubble are coming because of the as the liquid velocity is very high or gas velocity is very high from the bottom, so it is created some pressure inside the whole mixture and it will create this kind of bubble. So that is bubbling bed or slugging. If the bed is very tall, that is slugging. So this one is the circulating fluidized bed. So this is the showing the industry for circulating fluidized bed. And drop. So you can, I think you can see the written what is written. The fuel in massive high temperature flame Febby technology relies circulating not hot solids and effectively burn the fuel in a flameless combustion process. Its low uniform combustion temperature minimizes the formation of nitrogen oxide and allows the injection of limestone to capture acid gases. So this is a particular process they are showing, but this is how the circulating bed will work. So you can see that there are two extra portion of this circulating bed which is not there in case of plain fluidized bed. So with the help of this, they are maintaining the temperature. With the help of this, they are maintaining the temperature and the mixing will be good. Heat efficiently throughout the entire burner while fouling and corrosion are minimized. The payoff low plant emissions, low maintenance and high plant reliability. So these extra things will help in good combustion, heat efficiently and economically feasible. So this is a circulating fluidized bed. Then this is the pneumatic one. Pneumatic one means all the particles are out and it is creating a homogeneous kind of mixture. Very less amount of solids are left inside the fluidized bed. So this is a filter. So this is for particular company structure, that is why they are showing it. Next one is the Next one is the horizontal. Horizontally or laterally staged fluidized bed. Or here the cross-current flow or cross-current contact will be happening between the solid particles and the gas particles. Solid particles and the gas particles. So you can see products are feeding, and from each portion there is some gas is coming for different purpose. Someone is drying and someone is for cooling, but it is a cross-current contacting method. So particles are dried, then cooled. So this is the example of a lateral staged bed, which is which uses cross current contact method. This one is the vertically staged bed. So all are the vertically staged bed we generally notice. So this is one of them. So you can see how the fluidization mixing is happening. So this one is the turbulent one. So here you can see that the velocity of the liquid is very high. So that is why it is creating a random kind of mixture, random kind chaotic motion inside the fluidized bed, which is the turbulent fluidized bed, which can be called turbulent fluidized bed. And this one is the sprouting
other
bed.
particles which are not falling in the path of the
This is the sprouting bed. So here you can see that from one portion the fluid flow is coming or gas flow is coming, and that is creating some kind of jet kind of thing inside the fluidized bed. And from the top portion, this phenomena is called the sprouting. So all at these are falling down, so that is the sprouting. This phenomena is called sprouting, so that is called sprouted bed or sprouted fluidized bed. Next, so some advantages or disadvantages of the fluidized bed. So first, inside the fluidized bed, what we'll see that solids and liquid mixtures are there, and they behave like a liquid. The solids particles also behave like a liquid, right? So that is why they are said that it is liquid-like behavior. Then it is easy to control. Rapid mixing, you are seeing that how fast they are mixing, solid particles are mixing with each other. So that is the rapid mixing. And because of the rapid mixing, uniform temperature is maintained throughout the fluidized bed, and as well as the concentration. Uniform concentration is maintained. This one is the first advantage. Second one is it resists the rapid temperature change. So if it is continuously mixed homogeneously, that will definitely reduce the rapid temperature change. So if we can reduce the rapid temperature change, that means our product will be good, right? So that is why fluidized beds are important. So it resists rapid temperature change, hence responses slowly to change in operating condition and avoids temperature runaway with exothermic reaction. Third one is the applicable for large and small scale operations. So you can see that it can be used in bigger industries also and small lab scale also. Next, heat and mass transfer rate are high, requiring smaller surface because we are using small solid particles. So small particles means its surface to volume ratio will be higher, and that will be more good or more advantageous for good heat and mass transfer throughout the bed. And you can see that it is a continuous operation and easy to process due to stable condition. These are the advantages. And now what are the disadvantages? So bubbling beds of fine particles are difficult to predict and are less efficient. So if in the bubbling bed very small particles are there, then it is difficult to handle the whole process. So if the particle size is a little bit bigger, then bubbling bed is good, but for very fine particles, it's difficult to handle. Then, so due to the rapid mixing, sometimes what happens, particle will break up after contacting with each other because they are rotating with such a speed, they might contact and damage each other. So that is why particle breakup is common. Pipe and vessel walls error due to the collision of the particles. So as well as so they can damage the particle as well as the pipe or vessel or inside the bed. They are doing these things. So that is why the bed wall can also be damaged due to the collision of the particles. And it sometimes created non-uniform flow pattern. So you can see in the turbulent fluidized bed, there is no particular flow pattern. So anything is going anywhere. So that will create non-uniform flow pattern, which might lead to inefficient mixing. So size and type of particles which can handle by this technique are limited. So we in the inside the fluidized bed you cannot control very big size particles. So the particle size and type of particles are limited. Due to the complexity of the fluidized bed behavior, there are often difficulties in attempting scale up from smaller scale to industrial scales. So this is also one type of advantage we have studied, and this is also another disadvantage also. Next are the applications. So it has huge applications in industry or in chemical processing, physical processing, in everywhere. So it is creating silicon production. For silicon production, it is applied in case of chemical and petrochemical like cracking, fluid catalytic cracking, combustion, physical operation, pharmaceutical. If everywhere fluidized bed can be used. So some of the examples of solid catalyzed gas phase reactions are fluid catalytic cracking, reforming, aniline production, chlorination, bromination, Fischer-Tropsch synthesis, phthalic anhydride production, nitrogen oxide or sulfur dioxide productions, polyethylene and polypropylene production. These are the solid catalyzed gas phase reaction. That means in the gas phase reaction, catalyst is used as solid and the whole process is done or inside a fluidized bed. And gas solid reactions are roasting, combustion, incineration, gasification, coking, pyrolysis, then calcination process, reduction of iron oxide. All these processes are gas and solid reaction between gas and solid, which are also done in the fluidized bed. So fluidized bed are used as a technical process which has ability to promote high levels of contact between gases and solids. You know, because you already know this because you have seen that how gas and solids are continuously in touch with each other. In fluidized bed, a characteristic set of basic properties can be utilized, indispensable to modern process and chemical engineering. These properties include extremely high surface area contact between fluid and solid per unit bed of volume. That is what I have said, because the solid particles are very small here. So their surface to volume ratio is very high, and that is why their contact is good. Then high relative velocities between the fluid and dispersed solid phase. So the relative velocities of particles and solids, you have seen that how fast they are. Then high level of intermixing of the particulate phase, frequent particle-particle and particle wall collision. So one example is the food processing industry. So food products like peas, sliced vegetables are also produced from the fluidized bed. The fluid used in the fluidized bed may also contain a fluid of catalytic type. That's why it is also used to catalyze the chemical reaction and improve the rate of reaction. So that is another advantage or application of fluidized bed. Fluidized beds are also used for efficient bulk drying of materials. So bulk drying comes under the physical operation of the fluidized bed application. This includes drying, coating, coating of the catalyst, granulation, heat treatment, annealing, blending, classification, adsorption, and roasting. So these are all the application of fluidized bed. So it increases in dryers, it increases the efficiency by allowing for the entire surface of the subject of the drying to the suspended and therefore exposed to air. This process can also be combined with heating and cooling as the application. So we have seen also a video of that continuous heating and cooling of the solid particles. Fluidized bed dryers used in drying of various materials such as powder, tablets, granules, coals, fertilizers, plastic material. Anything can be dried in the fluidized bed. This process is being used in the granulation of the pharmaceutical powders. Fluidized bed coater are used widely for coating of powders, granules, tablets, pellets, beds held in suspension of column of air. Fluidized bed coating is used for test masking, enteric release and barrier films on tablets and powders. Bottom spray coating is used for sustained release and enteric release products, also employed in non-pharmaceutical fields in comparison to their use in pharmaceutical fields, as there are numerous apparatus, process, and products parameters that affect the quality of final pharmaceutical products. So, its application is huge. Next, what is the FCC? That is the fluid bed catalytic cracking. So, it is an industrial process. What is that? We'll see. So, it is an refinery operations. Core component of modern refinery process about 1/3 of the crude oil produced worldwide. So, fluid catalytic cracking is a process of producing crude oil. So, it produces ethane, methane, propane, gasoline, diesel, and heavy fuel oils. And it happens in atmospheric pressure. So, you can see that this is a continuous process. So, gas is lifted in FCC, catalytic cracking is feeded, and reaction happens. Reactor vapors are taken out, then it comes to another reactor where combustion happens and flue gas is created, and this is a continuous process. Catalyst flows out of the regenerator and mixes with the hydrocarbon steam line. The reaction occurs quickly and the catalyst is deactivated by the reaction depositing solid carbon or coke on the surface of the catalyst. Then it is recycled back to the regenerator. Firstly, the deposited coke of the surface with air. That sounds complicated. There is a lot going on in the reactor and regenerator. So I see that gas and excessive feed is entering from here. Hot regenerated catalysts. So catalysts are reusable, so that is why they are regenerated in the last reactor and they are coming back to the equation. So heat is quickly causes the long chain hydrocarbons to crack, which is an endothermic reaction, and it will reduce the temperature. Steam coke forms on the surface of the catalyst and reduces the cyclone in the reactor disengage the catalyst from the hydrocarbon vapor stream and the vapor exit the top of the reactor. Now the catalyst collects above the spent slide valve and flows to the regenerator. This is one is the regenerator. Air enters the bottom of the regenerator and combusts with the carbon on the spent catalyst. The temperature in the regenerator is high enough that it auto ignites this combustion. Here the energy is increasing or temperature is increasing for the cracking. So this combustion is providing all the energy. So this is a continuous process of FCC. The flue gas exits the reactor, removed downstream, and heat is recovered before it is vented to the atmosphere. So the reactor here we are using in different phases. That is nothing but the fluidized bed reactor. Different kinds of fluidized bed reactor. In order to circulate the catalyst through the system. The FCC reactor is a high-risk process to operate as there is an oxygen-rich atmosphere in the regenerator connected to the reactor, which is a hydrocarbon-rich atmosphere operating at temperature above the temperature required for auto-ignition. The consequences for misdirecting air into the reactor or hydrocarbon into the regenerator are a fire or potential explosion. So that is a different thing. So main thing is in the FCC plant, the reactors are used that are fluidized bed reactor because here the gas is generated, gas is coming, but here the catalyst is a solid catalyst, which enhances the process. So this is a FCC, overall overview of FCC. Okay. Next question, what is the physical application of the fluidized bed? Among the following four options, which one is the physical application of fluidized bed? What is the physical application of fluidized bed?
Granulation.
Yes, the answer is granulation. The rest of the applications are chemical applications.
Hmm.
So what is granulation? Let's see. So feeds are charged inside the fluidized bed, which is a charging process. Then fluidization is happening because gas is coming from the constant air stream is coming from the bottom. And now spraying is happening, reproducible granulation process. So one particle is attached to the another particle and it creates granules of multiple particles. So after the formation of granule, there should be drying process. So finally they are drying, they are dried. Now fluidization is off and the dry particles are ready and it is ready for discharging. So these are the filters they use to maintain. This is a nozzle from where the spraying is happening. Atomizing air or liquid, both can be sprayed. So this is the whole granulation process. Next, the velocity where the frictional force between particle and fluid just counterbalances the weight of the particle is called what? The velocity where the frictional force between particles and fluid just counterbalances the weight of the particles is called what?
I don't.
So the answer is minimum fluidization velocity. At just minimum fluidization velocity, the frictional force between the particles and the fluid just counterbalances the weight of the particles. So it is the minimum fluidization velocity. At this velocity, all the particles are just suspended. That means this is the situation between fixed bed and the fluidized bed.
Oh,
So in the fixed bed, the particles are fixed, and in fluidized bed, all are moving in a all are moving. So the minimum fluidization means the particles are just suspended. Particles are just suspended inside the bed. So that moment is called the minimum fluidization velocity, and at this point, the frictional force between the particle and the fluid just counterbalances the weight of the particle. Next, what is the value of minimum fluidization void fraction for spherical particles? What is the value of minimum fluidization void fraction for spherical particles? So what is the value of minimum fluidization void fraction for spherical particles?
0.4 to 0.45.
Yes, 0.4 to 0.45. Next, what is Archimedes number? What is Archimedes number?
I don't know.
So from the minimum fluidization velocity derivation, what we'll see later, the Archimedes number is coming. The expression I am just writing here. It is rho F into rho P minus rho F into d P cube G by mu square. Mu square. So this is the expression of Archimedes number. How this is coming, we will see the derivation after some time. So rho F is the fluid density inside the fluidized bed. Rho P is the particle density. dP is the diameter of the particle, and G is the gravitational acceleration, and mu is the fluid viscosity. So this is the expression of Archimedes number, or it can be called as Galileo number. Galileo number. Next, voidage at the onset of fluidization. Voidage at the onset of fluidization may be considerably greater than the packed bed voidage. Is it true or false? Voidage at the onset of fluidization may be considerably greater than the packed bed voidage. Is it true or false?
I don't.
So the answer is
True.
true, because void in the packed bed, what happens? The particles are stacked with each other. Particles are stacked in a certain place, and there is not much space between the particles. So here the void fraction is high for the solid particle, and here in the at the minimum fluidization or onset of fluidization, the particle are less because they are just suspended inside the fluid, right? So that is why the distance between, that means the void space, voidage is greater in case of onset of fluidization. Here the void space is less, so it is true. Next, what is the value of sphericity for sharp particles? What is the value of sphericity for sharp particles? What is the value of sphericity for sharp particles?
0.60 micrometer.
1.
Hmm.
0.67.
6.7. No, sorry. 6.7.
Yes, 0.67 is the sphericity for sharp particles. And this is for sharp particles. 0.86 is for round particles. And for coal, it is
Control.
0.63. Next, what are the factors affecting minimum fluidization velocity? What are the factors affecting minimum fluidization velocity?
Bed diameter, particle size,
Yes.
height.
So yes. So first one is the geometric. Second one is the physical properties. And last one is the thermodynamic conditions. So in the geometric variables, the bed diameter, bed height, particle size, and hole diameter is important. In the physical condition, in the physical properties, the fluid density, fluid viscosity, all the fluid properties are important in the physical condition. Then fluid surface tension and the slurry concentration. These are important for the physical properties. And in case of thermodynamic property, that means temperature, how much temperature the fluidized bed is maintained and at what pressure it is maintained. These are the important for thermodynamic condition. Next.
Ma'am, please solve the assignment.
Okay. So we'll come back it later. First, so which one?
Question number 5, 6, 7, and 10.
Okay, so this 6 almost in the class notes also there is a problem exactly look like 6. So you can solve it from there also. Still, I will solve it. A fluidization operation is to be executed in a 1 meter high fluidized bed with 2 millimeter particles by an oil. Its density and viscosities are given. If at point of incipient fluidization, the bed porosity and pressure drop across the bed is 10, calculate the density of the particles. So, the drop is 10 kPa. So, from so it is told that delta P is given as 10 kPa. So delta P is the given as 10 kPa. L is 1 meter height. Bed height is 1 meter. Then then solid particle density is given. Yes. No, calculate particle density. Okay. So fluid oil density is given, that is rho F is given, that is 900 kg per meter cube, and bed porosity is given, which is 39%. Bed porosity is given, which is 39%. So this is 39% 0.39. So rho S needs to be calculated. So from the minimum fluidization formula, we can apply delta L 1 minus epsilon because it is said that at the onset at this minimum fluidization conditions, right? So we can apply this condition. Yes, rho S minus rho F into G. So if we put all the values, so what will happen? So delta P is 10 kPa, suppose 10 into 10 cube. This is 1. 1 minus 0.39. Rho S needs to be calculated. This is 900. G is 9.81. So if you see how much is it coming? Yes, it is coming 2572, right? So rho is coming as 2571.09, almost 2572 kg per meter cube. So this is the answer, 2572. Option C. Okay, so this is the question number 5. Question number 7 is a bed of spherical particles, specific gravity
Ma'am, 6.
2.5. Yes, yes. 2.5 of uniform size is to be fluidized in a fluidized bed at a minimum fluidization velocity. At this minimum condition, the porosity is 0.4. Argon equation for the above particle fluid system in the fluidized bed at minimum fluidized condition is expressed as this, and if water is to be used as the fluidizing medium, then the minimum fluidization velocity wants to be calculated. So just a minute. Okay, so first we need to calculate the minimum fluidization velocity, that is delta P by L. So for delta P by L, from the expression we have known that it is 1 minus epsilon mf, that is the porosity, rho s minus rho f into g. This is the expression. So pressure drop is given as, pressure drop needs to be calculated, sorry. So first one is the water is given, right? So here the fluid is water and spherical particle is, so first porosity is given as 0.4. So 1 minus 0.4. Rho s is the solid particle. For solid particle, the specific gravity is given, right? Specific gravity is given. This is nothing but specific gravity is equals to density of the particle divided by density of the water. So what will be the density of the particle? It will be specific gravity, that is 2.5, and density of water, that is 1000, right? So that is 2500 kg per meter cube is the density of the particle. So rho s will be 2500 and fluid is already known, that is water, that is 1000. G is 9.81. Okay, did you get it? How is it coming? the specific, the row of the particle, how is it coming? Did you get it?
Yes, ma'am.
Yes. So now you know the delta P by L, what is it? So 2500 minus 1000 into 0.6 into 9.81. That is 8829. 8829 Pascal per length. Pascal per meter. Yes. So this is the first step. So from the now we will do the equation that is given. So the equation is given as delta P by L. Our delta P by L is known, that is 8829, right? Now 375 into, what is the value? 10 cube UMF plus 10.94 into 10 to the power 6 UMF square. 10.94 into 10 to the power 6 UMF square. So this is the equation, right? So you can solve from Sridharacharya equation, right? So we can just write it in this way. So you know, right? The equation is ax square plus bx plus c equals to 0. You know how to solve it, right? X equals to minus b plus minus b square minus 4ac by 2a. We will apply the same equation here. So in our case, x is the UMF, minus b means second one. So minus 375 into 10 cube, then plus minus root under b square is 375 into 10 cube whole square, minus 4, a is 10.94 into 10 to the power 6 into AC is 8829, right? And divided by 2 into A, that is 10.94 into 10 to the power 6. Now what we will get, that is your answer. So can you calculate that?
Okay.
So how much it will come? Let's calculate. How much is it coming?
My answer
Yes,
is
just a minute.
0.0054 0.0054
Hmm.
per second.
Just a minute. I need to calculate. Okay, so I did a mistake, that is why it is not coming. It is a square b plus c form na, so this will be minus 8829. So if you write it, then it will be clear. So in our case, a is 10.94 into 10 to the power 6. B is 375 into 10 cube, and C is minus 8829. Okay, minus 8829, that is why here it will be plus. So now you will get it. So 375 into yes, so it is coming 0.016 meter per second, right? Velocity, that means if you multiply it 1000, that will 16 millimeter per second. So 16 millimeter per second is the answer, I think.
Okay.
Yes, so 16 millimeter per second is the answer.
Name last 10.
Last 10. Okay. So it is written, a froth flotation experiment was conducted to recover copper sulfide from an ore. The experiment was carried out at 25 degrees centigrade. Assume the flotation process follows first order kinetics. After the experiment, 50% copper sulfide is recovered in 5 minutes. Calculate the flotation time required to recover 75% of the copper sulfide. Okay, that is easy. So if you go through the flotation slide, you will get a formula which is recovery R equals to R infinity 1 minus e to the power minus kt, right?
Okay.
If you go through the slides, you will get. So this one is 5-1, right? 5, this is 10. If you go through the lecture very carefully, you will get. So R is the recovery time. Recovery time. R infinity is the uh, recovery time. It is recovered, just recovery. It is recovery after infinite time. That is R infinity. K is the flotation rate of constant, and T is the time. So it is written in the question that R infinity maximum fractional recovery is 1, right? So R infinity is 1. So our equation becomes, so R infinity is 1. So our equation becomes R into 1 minus e to the power minus k into t. Okay. So first it is said that after the experiment, 50% copper sulfide is recovered in 5 minutes. So that means 50% means 0.5, right, equals to 1 minus e to the power minus k. K we don't know, and this is 5. 5 minutes, that is t is in 5. So from here we can calculate the k. How will you calculate? So we'll take this in one side, e to the power minus 5k equals to 1 minus 0.5. So we'll take logarithm. It will give minus 5k equals to ln of 1 minus 0.5. So now the k you can calculate. So ln 0.5 divided by 5. So it is coming as 0.1386 flotation per second, or this is in per second. Okay, so now from the first portion of the problem you have got the k. Now in the second portion it is asked to calculate the time. So here it is told the recovery is of 75%, and it is happening for the same element, that is copper sulfide. So k will be same, right? So in the second portion, in the second case, R is 0.75, 1 minus e to the power minus 0.1386, that is k, and we need to calculate the time, right? So similarly, we will calculate it. E into minus 0.1386, t is 1 minus 0.5, that is 0.25. Now from here we will calculate. This is coming as, t is coming as almost 10, that is 10 minutes. So this is the answer. 10 minutes is the answer. You got it? How I did? Right?
Okay, thank you.
Okay. Now we'll go back to our questions.
Ma'am, my assignment is mainly numerical problem are different wrong हो जाते हैं मैम.
What? I did not get.
इसी 10 आया तो कैलकुलेशन में मिस्टेक हो तो 8 भी आ सकता है, बस ये थोड़ा डिफरेंस.
Okay,
ये मैं
so yeah. So calculation should be should be correct, otherwise it will be confusing.
ओके ओके.
So you can do calculation in the calculator. There should not be any mistake.
ओके.
Okay. So the
मैम
question is,
ये
yes.
all assignment are solution not uploaded in the NPTEL. Only 2 or 3 assignment are uploaded.
Solutions are uploaded or not, I don't know. They give the answers, right?
Yes.
They just give the answer, but they don't give a solution.
Okay.
So solutions can be done because the problems they are giving in all from the course only, like the teacher what has he's taught, the questions are coming from there only. So I think that is why they are not giving the solution.
Okay.
Yes. Okay. So proceeding to the next question. So froth flotation is dependent upon what?
Flocculant and coagulant.
That is the Not exactly it is dependent. It is dependent on the material and the hydrophobic nature of the flocculants and coagulants. So density of the flocculants and coagulants and its hydrophobic nature is important for froth flotation. If the particles are hydrophilic, then the froth flotation will not happen effectively as it should happen in case of hydrophobic nature. Okay, so this is the dependent. Next,
Okay.
uh, next, what is froth flotation? So we'll see a video here. So you'll come see that feed is coming from the left side, the air is coming from the middle, and it is creating a pulp flow. That is rotational pulp flow, and that is the froth is happening. So pulp flow is creating, then air is going like this, and here the hydrophobic nature of because of the hydrophobic nature of the coagulants, these small particles are getting attached with them, and that is that they are keep floating in the solution. So sulfides collected. This is the air bubbles. So the air bubbles are collecting all the sulfides. Now this air is lost, and these sulfides are coming back to the solution, and they are reattached with the next bubble. So this is a bubble coalescence. So it is a process separately that selectively separates the materials based upon whether they are hydrophilic or hydrophobic. So this is the separation, one kind of separation process which is done by the froth flotation. So this is froth flotation. So next, okay. So next is the minimum fluidization velocity derivation is there. So I think you will be able to do it because it is in the lecture itself. Or if I will get time, I will solve it later.
Okay.
Let's complete first. Next, small contact angle leads to weak bubble adhesion. Is it true or false? Small contact angle leads to weak bubble adhesion in case of froth flotation. So here it is. Suppose there is a substance and some drop is there, some water drop is there. So if it is staying on the substrate like this. Here the contact angle is less than 90 degree, right? Less than 90 degree. And suppose it is this hydrophobic surface and the water droplet is creating this kind of shape, and the angle is greater than 90 degree. This is the hydrophobic surface which has large contact angle, and this is the hydrophilic surface, which has less contact angle. And now from the opposite side, if some air bubbles are there, so air bubbles is coming from the opposite direction. So in case of air bubble, suppose this is a water droplet, this is a water droplet, and here it is air bubble. In case of air bubble, we will see when the bubble is hydrophobic or contact angle is here, the contact angle is small, and when the bubble creates a film kind of thing on the substrate, this is hydrophilic for the bubble, and it will create greater than 90 degrees. This is less than 90 degrees. This is for water droplet and this is for air bubble. So both are different. So I have asked about the bubble adhesion. So when the small contact angle is there, less particle will attach to the bubble. Okay, so that is why it is shown that small contact angle leads to weak bubble adhesion. So that is why it is true.
Hmm.
Yes. If it is larger contact angle, then more particle will be attached to the bubble, and that will lead to more bubble adhesion.
Okay.
Next, discuss the steps of the particle flotation. So in case of particle flotation, first what happens? First, you have seen the video. In the video, first one is the, if you remember, the first one is the introduction of gas bubbles into the slurry. This is the first step. Next, the collision between the gas bubbles and the suspended matter which needs to be floated. Suppose there is some dart particles inside a water beaker or water filter, so we need to separate the dart particles. So froth flotation or particle flotation can be a method. So here we are sending some kind of air bubbles there, and air bubbles will collide with these dart particles which are floated, suspended inside the water. This is the second step. Next is the attachment of the bubbles to the surface of the suspended matter. That means these dust particles or dart particles will be attached on the surface of the bubbles, the way you have seen in the videos. This is the third step. Fourth one is collision between gas attached suspended particles and with the formation of the agglomerates. So now these dart particles are attached with the air bubbles, so they will create collision among themselves. This is the fourth step. Fifth one is the entrapment of more gas bubbles in the agglomerates. and the final one is the upward rise of the flock structures or agglomerates in a sweeping action. So here suppose this is a cloth beaker. So there are dart particle inside the water and some air bubbles are sent to here, inside here. So these dart particles will get attached on the air bubbles and they will again attach with other air bubbles. So and that way more entrampment of the gas bubbles will happen and finally they will together rise upward in the upward direction for finally removing the dart particles from the clear water. This is the froth flotation.
Okay.
Next, the reagents which are used to make the mineral surface hydrophobic are called what? The reagents which
Collecting.
are, yes, this is the collector. So the mineral surface should be hydrophobic. That is why the collectors are used. Collectors are nothing but some surfactants. Next, what are modulating agents? What are modulating agents? So there are three types of modulating agents. First one is the activators.
Depresent.
Yes.
pH regulator.
Next one is the depressants. And third one is the pH regulators. They different ways they help in the froth flotation to maintain the collectors and frothers and to maintain the process of the whole froth flotation. These activators and depressants are required. So activators are the chemical compounds which interact at the mineral surface to promote the interaction with the collector. And depressants are also the chemical compounds which alter the mineral surface to prevent or hinder the action of the collectors. And pH regulators is important for determining the pH of the selective separation of minerals. So these are some of the modulating agents. Next, what are used to raise and lower pH of a solution? So soda ash or lime.
Carbonate.
Yes. Soda ash means the sodium carbonate, that is Na2CO3, and lime is calcium oxide, CaO.
Oxide.
These are used to raise pH, and for lowering the pH, sulfuric acid, that is acid, obviously acid would be used. This is used to lower the pH. Next, difference between flocculation and coagulation. So you can see a video from the So here you can see that flocculation, first flocculant is given. So they will show it differently. Just right. Crucial steps in water treatment to remove impurities and particles from water. So this is a treatment tank and mixer fill the tank with the water. First one is the coagulation process. Untreated water, some particles will settle down due to large size by gravity, but tiny suspended particles will not settle down easily. So to settle them down, we need to add coagulant. So alum is used as coagulant inside the tank. And now the agitator is used for the high mixing and make the solution homogeneous. After you see, after mixing stop, the agitator, the coagulant reacts with suspended particles and will make microflux. So the particles which are suspended individually, after the mixing, they will come together and create micro sized flux. This is the coagulation. Now, if the suspended particles become micro size, then it is easy to separate them, right? Because their size is now bigger and they will settle down at the bottom. And in case of flocculation, polymer is taken as flocculant and agitators are turned out. So it will allow the flocks to grow in size and settle down in a few minutes. So coagulation is helping to create the microflux and flocculation is helping to settle down these microflux. Okay, so this is a basic difference. There are maybe other difference also, but we'll not look into much on that. Next, what is the percentage of lead in a grade solution? What is the percentage of lead in a lead on a grade solution? The answer is 65.3. In a grade is a material where this metal, this lead is there as a 65.3% content. Next, this is what is the example of ores. What are the different types of ores used in the flotation in industry? So mainly there are two types of. First one is the lead zinc ores, and second one is the copper ores. So there are some division also. So there are PBS is one of the lead zinc ores, PbCO3, PbSO4, PbSb, PbAs, PbBi, PbCrO4. There are different types of lead-based ores. And in copper based, there is copper sulfide, that is Cu2s, CuS, CuFeS2, CuSFeS4, etc. These are the copper ores. Next question is one of the naturally hydrophobic minerals that is now concentrated on a very large scale flotation, which is used as one of the naturally hydrophobic minerals that is now concentrated on a very large scale flotation. which is used as one of the naturally hydrophobic minerals that is now concentrated on a very large scale flotation? The answer is coal. Coal is naturally hydrophobic material used in flotation. Next question is, what is the recovery of flotation? So just recovery we have learned that how is it coming? We can see that suppose in chemical reaction engineering we will see that how a reaction occurs. If it is a first order reaction, then how a reaction occurs, what is the rate constant, and at what time the reaction finishes, that is dependent on the rate constant or reaction mechanism. So it is also coming from here. So for generally the general rate equation is given as minus dc dt into k c to the power n. C is the concentration of the material, n is the order, C is the concentration, T is time, and R is the rate constant. In this case, it is the flotation rate constant. So if it is a first order reaction, if n is 1, then you know that minus dc dt equals to kc, right? So if we integrate it, and integrate from where? Suppose at initial time when that process has not started, the concentration is C0, and after when the mechanism or reaction ends after time t, the equation becomes C. So if we integrate this equation from C0 to C, I think you know the integration. So if you integrate it from 0 to t time and from C0 concentration to C, we will get a general equation which is C equals to C0 e to the power minus kt. That is the integration. That is integration formula. So now recovery comes. So recovery means what is expended, what is left. So initially the concentration was C0 and now left is C, and with respect to C0, that is the recovery. So if you just simplify it, it will be 1 minus C by C0, and it will be 1 minus C by C0. From here you can write it as C by C0 equals to e to the power minus kt, right? So it is e to the power minus kt.
Okay, ma'am. Thank you.
Yes. I'll be doing some more problem. You can watch it later.
Okay. Thank you.
Okay.
Thank you, ma'am.
Yes. Okay. So if we consider that after infinite time, that means t infinity, recovery is R infinity. So we will there is a graph of time versus recovery. So we'll consider it at it is 0 and it is 1. So after infinite time, recovery is 1. So we'll consider R infinity equals to 1. So from there we can say that R equals to recovery is 1 minus R infinity into 1 minus e to the power minus kt. This is the general equation of recovery for flotation. Okay. So one thing is left before, that is the derivation of the minimum fluidization velocity, right? Derivation of the minimum fluidization velocity. So you have known that in minimum fluidization velocity, what is written, that the condition, the viscosity, the velocity, at this velocity, the frictional force between the particles and the fluid just counterbalances the weight of the particles, right? Counterbalances the weight of the particles. So that means this is drag force at the upward direction. Drag force by upward moving gas will be equals to apparent weight of the particles. So drag force means the pressure into area equals to, this is apparent weight, means the area of the particle, the length of the bed at minimum fluidization condition, the bed porosity, the density difference between the particle solid and the fluid, and its density, its gravitational acceleration, right? Now if we simplify, what will come? It will be coming as Pb by delta Pb by LMF equals to 1 minus epsilon mf into rho s minus rho g into g. This is the expression of pressure drop per unit length at the minimum fluidization condition. Okay. Next comes, so this minimum fluidization, so from the Argand equation in earlier week we have seen the, from Argand equation, the pressure drop for minimum fluidization condition will be 151 minus epsilon mf square divided by epsilon mf cube mu into u divided by phi s square dp square plus 1.75 into 1 minus epsilon mf by epsilon mf into rho g u square by phi s dp. So this is the Argand equation based on the minimum fluidization velocity, right? So here you can write it as UMF also, because we are considering the minimum fluidization condition. So now if we bring the expression of this delta Pb by LMF, which is 1 minus epsilon mf into rho s minus rho g into g equals to, the right hand side is same, 150 So this is the expression of Argan equation, right? Next, we will divide it by a factor. So divide by 1 minus epsilon mf into dp cube rho f mu square, because we need to simplify this big equation, right? So that is why we are dividing with this factor. And now what will come? Suppose we are dividing the right hand side first. So what is left? 150 into 1 minus epsilon mf divided by epsilon mf cube pi a square. Now in the denominator, rho f is coming. Rho f or rho g is same here. Okay, I might have written rho f somewhere else, rho g somewhere else. So it is the gas or fluid velocity. Okay, they both are same. Don't confuse. Okay, both are same. So now one rho f will be coming here. Mu UMF is already there, and 1 dP is coming in the numerator, right? And at the bottom 1 mu is coming, because rest of the parties get cancelled. This is the first term. Second term is similarly 1.75 into 1 by epsilon mf into phi s, right? And what is left? So there is already a rho f, so it will be rho f square UMF square, and there is 1 dP in the denominator, so dP square will be left, and at the bottom there is mu square, right? And equals to the left hand side. The left hand side, what is there? 1 minus epsilon mf will be cancelled out. Then what is left? dP cube rho f, rho s minus rho f, or this is also rho f. Okay. Not rho g and rho f are same, so whatever I write doesn't matter. Here also rho f will be there. Rho s minus rho f into g, and at the bottom there is mu square. So this is the simplification version after divide. Now what can we write? So if you notice this portion, this is what? This is nothing but Reynolds number, right? Rho u dP by mu, right? At the minimum fluidization condition. This is also rho square mu uf square dP square by mu square. That means Reynolds number at minimum fluidization square whole square. And the last portion is called the right hand side is called the Archimedes number. The whole term is called the Archimedes number. So if we simplify it, we can write it like this: 1.75 phi s epsilon mf cube there is epsilon mf cube. Here is also there, here and here. So 1.75 by phi s epsilon mf cube. Then what is that? REMF whole square, right? So it will be REMF whole square plus 150 into 1 minus epsilon mf divided by epsilon mf cube phi a square into Re Reynolds number at minimum fluidization condition equals to Archimedes number, right? So from the now we can write it simplifically, right? K1, suppose this is K1, this is K1, this is K2. Okay, so K1 REMF square plus K2 REMF equals to AR. So this is nothing but a quadratic equation which needs to be solved by Sridhar Acharya, and here REMF will be minus K2 plus minus K2 square minus or plus 4K1 AR divided by 2K1, right? So from here we'll get the Reynolds number, and from Reynolds number we'll get the minimum fluidization velocity, because it is the expression of minimum fluidization velocity. So here we'll get the minimum fluidization velocity expression, right? Okay. So this is the expression. Now we'll do some extra problem which I will be telling. So very fast we'll do some problem, easy problem. So very fast we'll do some problems. So first one, a 0.5 meter height bed of 1 millimeter diameter glass sphere density 2500 kg per meter cube is to be fluidized by water. Okay, if at the point of incipient fluidization the bed voidage is 40%, calculate the pressure drop across the bed. Okay, this is very simple. So from the simple formula we'll use del P by L equals to 1 minus epsilon minimum fluidization condition rho S minus rho F into G, right? So delta P needs to be calculated. So epsilon is given as 40%, that means 1 minus 0.4. Solid density is 2500, water density is 1000, G is 9.81 and delta L is 0.5, right? Which is nothing but 4414, right? 4414.5 Pascal equals to 4.4 kilopascal. This is the first problem. Okay, this is a simple, very simple problem. Next one. So here I am writing the important things only. Okay. So pressure drop in an air fluidized bed of catalyst particles. So its particle density is given, that is rho p is 2000 kg per meter cube, and diameter of the particle is 0.05 centimeter. I am not writing the whole problem. You can write also. So catalyst particles of 60 centimeter bed depth, that is L is 60 centimeter, and bed porosity is, so that is epsilon is 0.5. Now calculate the pressure drop in centimeter of water. So calculate the pressure drop in centimeter of water. So similarly the problem will happen. So what is delta P needs to be calculated, 1 minus epsilon rho P minus rho F into G into L. So it is 1 minus 0.5, rho P is 2000, air fluidized bed, right? So air density is 1.23. We know G is 9.81 and L is 0.6. That is 60 centimeter means 0.6 meter. So what will it come? So it is coming as 5882.38 Pascal. Now it is said in the calculate the pressure drop in centimeter of water. So also we know delta P is rho GH. So it is 5. So we need to calculate the H, right? So H will be delta P by rho of water into G. So delta P is 5882.38, rho of water is 1000 into 9.81. So it is 0.5996 meter, which is 59.96 centimeter, which is almost 60 centimeter. So this is the answer. Okay. Okay. Last problem. So this problem needs to be written. So a bed fluidized by water is used for cleaning sand contaminate with salts. Okay. The particle of sand and salt having the same shape and size but different density. Okay, so row of sand is 2500 kg per meter cube and row of sand is row of salt is 2000 kg per meter cube. If the initial volume fraction of salt in the mixture is 0.3 and if the initial minimum fluidization velocity is 0.9 meter per second, find the final value of UMF, that is minimum fluidization velocity in meter per second when the sand is washed free of salt. Assume that the bed characteristic, that is bed porosity and bed surface area per unit length do not change during the operation and the pressure drop per unit length is directly proportional to the fluid velocity. Okay, so this is a big problem. Let's do it. It's not a big problem. Actually, the question is big, but not the equation or the solution. So for the minimum velocity, we know that delta P by L equals to 1 minus epsilon rho P minus rho F into G. In the question, it is said that delta P by L pressure drop per unit length will be proportional to the fluid velocity. It is proportional to the fluid velocity, that is UMF, suppose. So this thing 1 minus epsilon rho P minus rho F into G will also be proportional to UMF, right? So you know that G is a constant and porosity of the bed is also constant. In the equation it is said. So rho P minus rho F will be proportional to UMF. So density difference will be proportional. Density difference will be proportional to minimum fluidization velocity. So now what we can write? Say that UMF2 by UMF1 equals to rho P2 by rho F by rho P1 by rho F. Right? So the connection between the density difference of the particles and fluids with the minimum fluidization is this. So we need to calculate finally the minimum fluidization. So rho P1 is the average density according to the given sand and salt fraction. So initially, initially in the fluidized bed, both sand and salt are there, but their volume fraction is different, right? So initially, volume fraction, this is the salt density and salt volume fraction initially plus sand density into sand volume fraction. So initially what will happen? Salt density is 2000 and salt volume fraction is 0.3 plus this is 2500 into 0.7, right? So it is 0.3, that means sand fraction will be 0.7. So it will coming as 2350. So initially the particle density in the fluidized bed is 2350 kg per meter cube. Next, rho P2. Rho P2 is the condition where the salt is washed away. The salt is totally washed away, right? It is written that the sand is washed free of salt. Though salt is washed away, so only the concentration, only the particle left is sand. That is the sand density, which is nothing but 2500 kg per meter cube. Now we'll come to the equation, and another one is rho F, right? Rho F is the water. So water density is nothing but 1000 kg per meter cube. Initially, the minimum fluidization velocity is given as, in the question you will see, initial minimum fluidization velocity is 0.9 meter per second. So everything is given according to the equation, right? This equation, everything is known. Only the UMF2 needs to be calculated, which is our equation. So UMF2 divided by 0.9 equals to 2500 minus 1000 divided by 2350 minus 1000, right? So now minimum fluidization velocity in the second case will be 1 meter per second is our answer. Okay. So when the salt is washed away, only the sand is left, the minimum fluidization velocity will be 1 meter per second. Okay. So that is from my side today. I hope today's lecture is helpful to you, and you will be able to solve the left assignments. I have already solved the equations or the problems. So we'll meet on next Saturday. Till then, goodbye.